In front of me here, I have some more complicated limits, and I know their answers, but if I were to prove them using epsilon-delta, that would be a very, very tedious and difficult task. So does that mean that for any limit that we ever encounter, we always have to prove that it's true using epsilon-delta? Thankfully, no, because honestly, who wants to do that? Instead, we have what are called limit laws, which I've presented here. And there's a lot of them, and we're going to quickly go through them, and then we're going to prove a few of them. What the first one says is that a limit of a constant is just a constant, which makes sense, it's a horizontal line, so the values are all going to be the same everywhere. The limit of a constant times a function is equal to the constant times the limit of a function, so we're going to prove both of these. We're going to prove that the limit as x goes to c of just the linear function x is c, and we're going to prove sum and difference rules. So the limit as x goes to c of a sum of two functions is equal to the sum of the limits. But then there's also other ones, like the limit of the product of functions is just the product of the limits. The limit of the quotient is the quotient of the limits, where as long as the limit of the bottom function is not equal to 0. We have an exponential rule, and we have an nth root rule, which has some more other caveats, so you can pause the video if you want to look at those. And then we have the polynomial rule, where polynomials are just continuous everywhere, which means that you just plug in that value of c and you're good to go. Again, this is just a scary looking expression for polynomials, it's just a sum of all the terms with coefficients. Okay, so let's go on to prove the first one. The limit as x goes to c of some constant k should be equal to k. Okay, and how do you think we're going to prove these? We're going to use epsilon-delta so that we don't have to later. So I'm going to bring this down, and we're going to prove that this is true. Okay, so of course our function f of x is going to be equal to that constant k, and the limit should be equal to k. So let's say for all epsilon greater than 0, there exists a delta greater than 0 such that when 0 is less than the distance of x minus c to delta is going to imply that the distance between the function f of x, which is in this case k, from the limit k has to be less than epsilon. Now of course you can see that the k's here cancel and they become 0. So absolute value of 0 is 0, so I have 0 less than epsilon. What this means is that for all values of x, such that x is within delta of the value it's approaching, epsilon is greater than 0, which is our initial condition that epsilon is greater than 0. So technically, we actually do not need to do anything else other than just say, choose delta to be anything that's greater than 0. That's it. Because it's true for all positive delta. Okay, that was easy enough. Let's move on. Now we're going to show this slightly more advanced, but still rather simple property. The limit of a constant times a function is just a constant times the limit of the function without the constant. So we're going to bring that down right here. All right, so how do you go about proving this? Well, it's not bad either, all right? Let's go and do it. So, again, for all epsilon greater than 0, or actually before I do that, let me just say, let's call the limit as x goes to c of f of x L. So basically, the limit as x goes to c of k f of x is just equal to KL, all right? So then, we start saying for all epsilon greater than 0, there is a delta, right, that's greater than 0, such that, and now we have 0 less than x minus c is less than delta, which will imply for us that we get f of x minus L is going to be less than, and since we can choose any epsilon we want, let's just call it epsilon over the absolute value of our constant k. Unrelated for now, but we're going to show that we can relate these two together. So now let's choose some other delta, delta 1, equal to our original delta. And now we're going to set that aside and we're going to find out what we want to show. In these kind of proofs, we want to show, we write WTS for want to show, and we can now consider that 0 is less than absolute value of x minus c is less than that delta we chose above, will imply that kf of x, right, minus KL is less than epsilon, all right? That's the second part here. Kf of x minus KL is going to be less than epsilon, all right? So we use this part here in the first beginning of our definition, and now we're going to use this side and prove that it's equal to this side, all right? So let's get on with it. We can, of course, factor out a k here, and we get an absolute value of k times f of x minus L is less than epsilon, and we get that absolute value of f of x minus L is going to be less than epsilon over absolute value of k. All right, which means we're done. Because when we multiply k on both sides, that's just going to be less than epsilon, which was what we wanted to show. So we've just proved that. All right, now let's prove the limit of the linear function. So limit as x goes to c of x is equal to c. All right, so how do we prove that? Well, again, f of x is our function x, so we can say for all epsilon greater than 0, there is a delta greater than 0 such that, and now again, you know the drill. We have the distance between x and c is going to be within delta, and that'll imply that the distance between our function, which is x, right, and the limit c is less than epsilon. Now look at this. This is the same statement, right? X minus c less than delta implies x minus c is less than epsilon, which means if we choose delta to equal epsilon, then this assumption still holds. So if we let delta equal epsilon, then absolute value of x minus c is less than epsilon, which is what we want to show right away, and we're done. So that's it. Okay. Now, let's move on to the sum rule, okay? Which again, we're going to go back and look at what that actually says. It says the limit of the sums is the sum of the limit, all right? And we're going to show that real quickly. And this is going to be a little bit more of a complicated proof than the other one, but bear with me, okay? So let's just call the limit as x goes to c of f of x L, and let's call the limit as x goes to c of g of x M. So what we want to show is that this limit is going to be equal to the sum of these two values. All right, let's now use the epsilon-delta definition twice. Why twice? Well, let me show you. We can say for all epsilon 1 greater than 0, or just epsilon in this case, and you'll see why, there is a delta 1 greater than 0, such that when x is within delta of c, we can say that the distance between our function f of x and the limit L, right, will be within epsilon over 2, all right? And why do I add this 2 over here? Because remember, it should be for all epsilon greater than 0. So we should be able to choose any epsilon we want and get a corresponding delta. So epsilon over 2 versus epsilon over 1 doesn't really matter, but epsilon over 2 will be convenient. You'll see later why. So I forgot to add the 1 here. Okay, then we can say for the same epsilon greater than 0, or just for all epsilon greater than 0, there also exists a delta 2 greater than 0, such that when, again, x is within delta 2 of c, we can say that the distance between g of x, our new function, from its value m, will be less than epsilon over 2. Okay, at this point, we want to consider what we were actually trying to equate. We want to show, using the definition of epsilon delta, that f of x plus g of x minus L minus m will be less than epsilon, or some value of epsilon. So how do we add those two equations together? Well, if we choose a third delta, delta 3, to be the minimum, or actually less than or equal to, if you will, the minimum value, called min, is a horrible bracket, of delta 1 and delta 2, which just means that it'll just choose whichever one is smaller of these two at any moment, right, for any of their epsilon, then we could say that 0 less than x minus c less than delta 3 implies. And now we're going to set that aside, and we're going to consider what we mean when what we want to show, right? We want to show that this will be less than some value of epsilon. So we can consider absolute value f of x plus g of x, right, minus L minus m, right? Because that's essentially what we're trying to show in the absolute value form. This is just the difference between, this is just the distance between the sum of the limits and the sum of the functions, right? Okay, so what is this equal to? Well, we can rearrange this to become f of x minus L plus g of x minus m. And now let's recall a very important absolute value property, that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This is called the triangle inequality. And it's an incredibly important result in mathematics. And this is very important for epsilon-delta proofs and absolute value ideas in general. So we're going to use that. If f of x minus L plus g of x minus m is less than or equal to, right, so we can say it's less than or equal to by the triangle inequality, we can separate them together now. F of x minus L, close that bar, and add g of x minus m, right? But now, why do we want to do this? Because look, by the definitions that we established here, f of x minus L is less than epsilon over 2, and g of x minus m is less than epsilon over 2, which means that if this is less than epsilon over 2, and this is less than epsilon over 2, then if we add them together, they will both be less than epsilon on its own. Now this is important. Why is this important? Because we just showed what we wanted to show. We know that for any epsilon, so for all epsilon greater than 0, we can, and we found a delta 3 greater than 0, such that, and now we just kind of found out that when we have 0 less than x minus c is less than delta 3, that the limit of the sums is the sum of the limit. All right, because we started with this expression, and then we turned it into this expression, which means that they're the same, under the same x approaching the certain value. So we proved it. We can put QED down as proved. Okay, what about the difference rule? Well, that's not very different at all. Except in this case, all we're doing is we're saying L minus M, right? So f of x minus g of x, L minus M. And the only thing we're changing here is this idea over here. It'll be f of x minus g of x, all right? And then that's will be the distance from, so minus, in parentheses, L minus M, which is the same thing as minus L plus M. So what we do is when we rearrange it, we get f of x minus L minus g of x plus M, all right? And what happens in this case, I'm going to just reproduce it and bring it down because it's going to get a bit confusing soon if I don't. So let's see. Here we go. So we rearranged this and we found f of x minus L minus g of x plus M, because that's how the way we distributed the -1. So we can split this and into like this. By the triangle inequality, this is less than or equal to f of x minus L, and then we can add that to M minus g of x. All right? Now, M minus g of x is the same thing as saying negative g of x minus M. All right? Because you're just factoring out a -1 and switching their order. All right? Now, the important thing to note here is that the absolute value of any value is going to be the same as its regular absolute value. So absolute value of negative y is equal to absolute value of y. So we can essentially just get rid of that negative right there. And now we have the same expression as we had in part 1, or in the sum proof. So we know that this is going to be less than epsilon over 2, and this is going to be less than epsilon over 2. And we don't have to change our delta being the minimum, so this is going to be less than epsilon. And so the same proof arises from that. And so we can just put down a proof for that, QED. So now we know that the limit of the sum or difference of functions is going to be equal to the sum or difference of the limits. Now, this just scratches the surface of the proofs and the kind of limit laws in general. But there's so many of these, and there's many different ways to prove them. But the key is that the question is, why are they so important? Well, they're important so that you never have to use epsilon-delta again in your life. For example, the limit as x goes to 2 of the cube root of x squared plus 2x over 3x minus 4, all of this uses those limit laws. So for example, we can take the quotient rule and take this limit and put it over here and over here. And then we can separate them by doing the difference rule of limits. This is a constant which will hop out of the limit, and we'll get the limit of the function x. So we can just plug in 2. So essentially we can just plug in x equals 2 over here, and we get 3 times 2 minus 4 is 6 minus 4 is 2. So we get 2 over here. In here, we know that the nth root of a limit is just the limit to the nth of the nth root. So we can say that we can put the limit inside of this function, use the sum rule to separate these two, and then use the power rule with the second order exponent and the constant rule, and then simply plug in from there the idea of the limit as x going to c of x is equal to c. So essentially, we can plug in a 2 here and a 2 here, and so we get the ultimate answer is equal to cube root of 8 is 2 over 2, so it's 1. So this, I hope, is a good and fairly quick explanation of how important these limit rules are and that all limits you ever do will eventually boil down to the limit laws. Thanks for watching.